Hello and welcome to our pre-conference workshop on building water quality. In this workshop, there will be two presentations which will be paused at scheduled intervals for question and answer sessions. Let me introduce myself. My name is Hendrik van Genderen and I'm the Water Resources Engineer at the Water Authority in the Cayman Islands. I will be the moderator for this session today. I would like to thank our sponsors for the conference. We really appreciate the support of Sandpick Contracting Cayman Limited, Deal Metering, Maya, Water Engineering and Pipeline Company Limited, WEBCO, Consolidated Water Company Limited, DART Enterprises, Florida Aqua Store, and Argo American. I will now go over a few housekeeping rules. Except for the speaker's microphone, all other microphones will be muted. We also ask that apart from the speakers, everybody turns off their webcam. Throughout the presentation, you can submit questions via text in the Zoom chat, and we will do our best to answer all your questions. We will take short breaks for questions at intervals of approximately 20 minutes during the presentation. At that time, we take about 5 minutes to address written questions submitted from the audience. At the end of the presentation, there will be more time for further questions. This is a collaborative session where all in attendance will be able to engage in the discussion through the questions. Now, it is my pleasure to introduce both our guest speakers of today. Dr. Jennifer Clancy. Dr. Clancy is the Chief Scientist and Founding Fellow with the Environmental Science Policy and Research Institute, also known as ESPRI. She has worked on Legionella and Legionnaire's disease since 1980, both in clinical and environmental research and testing. After 35 years working with drinking water utilities on a host of water quality and treatment issues, her current focus is on water quality degradation in buildings and ways to manage opportunistic pathogens, including Legionella. In 2012, she was awarded the inaugural Water Research Foundation Research Innovation Award. And in 2014, the American Water Works Association recognized her contribution for excellence in water supply research with the AP Black Research Award. On a personal note, I know Jen, because that's how we call each other, for about 20 years. And she's part of what I would call the extended Water Authority family. She has played a key role in the accreditation process of the Water Authority Laboratory by conducting internal audits and providing general advice. She is also our go-to person when the Water Authority has water quality issues of biological nature. And I can tell you there are times that we call upon her. I'd like to also introduce Dr. Sheldon Masters. Dr. Sheldon Masters is an assistant professor at the University of Colorado, Boulder. His expertise is in distribution system water quality and pipeline corrosion. He has been involved in corrosion control treatment evaluations and conducted desktop, bench scale, and pilot studies to develop recommendations for improved corrosion control treatment. He works on building water quality issues related to both chemistry and microbiology. Sheldon was the principal investigator on a $2 million US EPA-funded study on occurrence of opportunistic pathogens, including Legionella, pneumophilia, and disinfection byproducts in experimental pipe loops and water heaters. He is a member of the AWWA Committee 514 on minimizing risk of injury and disease in building water systems. Also, on a personal note, I first met Sheldon 3 years ago when he came to Cayman with Jen for a similar workshop as he's been sharing with you, and I was really impressed with what he shared with you. I invite you to join the workshop and have a very good experience today. Jennifer, I turn it over to you. You can turn on your microphone and webcam and start your presentation.
Okay, great. Thank you, Henry. I think I'm on. I think everyone can hear me. Welcome, everyone. I can only say I wish we were all together in the Cayman Islands right now doing this, but maybe next time. I'm speaking to you this morning from my home in northern Vermont. I live about 12 miles south of the Canadian border, the Quebec border in the Northeast US. And as Henry said, I've been working on Legionella and Legionnaire's disease and building water quality issues for about 40 years now. So that's what I'll be talking specifically about today, but we'll give you kind of a whirlwind tour, starting with drinking water treatment, distribution systems, moving into buildings. Sheldon will present some of our case study work where we've actually gone out and worked in buildings with water quality problems, which is the focus of my work now and the focus of Sheldon's research. And then after we've scared everybody and talked about all these things that can happen in buildings, the program will switch back to me and we'll talk about building water management plans and how to prevent these types of problems. So let's get into it here. First of all, I'd like to thank CWWA and the Water Authority for inviting us to speak. As Henry said, you know, we go back a long time, and it's always great to be involved with this group and this organization. So we'll cover water treatment, microbiology, chemistry, get into buildings, then our examples. And so I thought about a way to introduce this. So I was thinking, you know, I think I need an elevator pitch. And then I said, I'm not sure what an elevator pitch is. So I looked it up. So it's an informal noun. It's a succinct and pervasive sales pitch. It's 30 seconds to 2 minutes, and it defines a process, an organization, event, something you're trying to convince someone to do, and the value proposition. So what is it that you're pitching, and why should I do this? Why should I be interested? So here's my building water quality elevator pitch. So our issue is water quality in buildings can go bad. Water quality declines rapidly, and that's because of stagnation in buildings, loss of disinfectant residual, low flow in buildings, and temperature. The problems can be anything from discolored water to disease leading to death. Legionnaire's disease, which is what I'll focus on, is currently the #1 cause of waterborne disease outbreaks in both the US and Canada, also in many European countries and Japan. So this is an increasing, expanding problem. But when this happens, when there are water quality issues in a building, what happens is people call the water utility because that's where they get the water from. But what the utility sends to your building is not what's being experienced at the tap. And it's because the conditions in the building, either the conditions themselves or the operation of the building plumbing, is what degrades the water quality. So the solution, you can fix this problem, and the solutions can be simple. And one of the ways we do this is to identify the hazards and mitigate hazards to maintain water quality. So the value proposition here is that you want to and you can fix this problem. You would do this to protect public health, maintain good standing in the community, certainly here in the United States, avoid costly and embarrassing lawsuits, and then also in the United States, maintain accreditation if you're a healthcare facility. We currently have regulations now in the US that any healthcare facility that receives federal government funding has to have a building water management plan. So that covers everything from hospitals to acute care facilities, nursing home, anyone that's basically providing medical care. So this workshop will provide a roadmap on how we do this. So one of the things we've seen over the course of years is the changing character of waterborne disease outbreaks. And this presentation will be US centric, but this covers most, you can think about this as being, pertinent to the developed world in general. So in the early 1900s, the majority of waterborne disease outbreaks were due to typhoid fever. And this graph on the left is just showing the death rate for typhoid fever in the US. And when chlorination began in about 1908, as soon as chlorination was introduced, those cases plummeted. And while we still have a few cases of typhoid fever, they're very low numbers of cases. They're individual cases and not outbreaks, and they're generally associated with international travel. So chlorine really changed the face of waterborne disease outbreaks in the US at the turn of the last century, 2 centuries ago, I guess. So now what we're looking at is not a new group of organisms. We refer to these as emerging drinking water pathogens. They've been around they've been around forever. They come from Mother Nature, but now we have a different focus. And one of the main features is these organisms are not fecal in origin. So while we've tried to control fecal contamination in water, now we're dealing with organisms that they occur naturally in water, and they're not they're part of the natural water cycle. They don't rely on human hosts to reproduce, like other things like Giardia, Cryptosporidium oocysts, bacteria like Salmonella. And importantly, drinking water treatment is not designed to control these organisms because they're part of the natural flora of water and soil. They'll be decreased in numbers through treatment, but many of these species, if you look for them, can be found in finished water, but just having them present there does not mean that they're going to cause problems. We don't monitor these organisms either in source or treated water. There aren't any regulations, at least in the US and Canada, where we monitor these on a regular basis. And even if we monitored for them, you would expect to find them at very low levels or non-detect levels. What happens after disinfection is that many of these opportunistic pathogens, particularly the Legionella and the mycobacteria, are particularly resistant to disinfection. So even after disinfection, you potentially can find some of these in drinking water. They establish themselves in distribution system biofilms, especially at distal ends of the system. And we refer to these as opportunistic premise plumbing pathogens. That's a mouthful, OPS. And there's Legionella that we've talked about. I'll talk briefly about non-tuberculous mycobacteria, or NTM, Pseudomonas aeruginosa, Naegleria fowleri, also known as the brain-eating amoeba, and free-living amoeba, which are also called free-living protozoa. So these things are naturally occurring in biofilm. They're generally occurring in low numbers, and they become a problem when they get into a building. They can become problems. So what this cartoon is showing you here is looking at what happens from source to treatment to the customer's tap. So we see water quality in the source water, depending on, for example, if you're a lake or a river, which is shown in the little cartoon. The source water is quality is significantly improved, both microbiologically and chemically, through treatment. So you go across, you see the treatment plant, you see that water quality is increased. So we're making potable water, making it safe for people to drink. But as we go through time and distance, there's a decay rate in that water quality. There'll be biofilm growth in the system. There may be some stagnation, loss of chlorine, and then ingress from leaks in pipes, pinhole leaks, that type of thing. So over time and distance, the water quality it'll be reduced in water quality. That happens in distribution, and certainly the water leaving the plant will have a certain residual. And when you get to the distal parts of the system, it's probably less. And when it gets into by the time it gets to the customer's tap, that is the water quality that the customer sees. But there's a lot that goes on in the building, and that's what we'll talk about next. That also leads to this decay in quality. So at least what happens in the US and I think in Canada, Sheldon, shake your head if regulations are the same in Canada, that the water quality, once it crosses the meter and gets into the building, the water supplier is not legally responsible for it. And the exception here is US EPA, the lead and copper rule, where we collect samples in homes to look at lead and copper levels. And I think that's the same in Canada. So except for that, once the water gets into the home, then it's no longer the utility's responsibility. What happens with building owners, though, they don't always know that the water quality degrades in their plumbing, or they don't know the degree to which it could degrade, that they're responsible for water quality in their building, or how to operate the system to maintain water quality. So for about the last 5 years, this is a focus of the work that Sheldon and I have done, is working with buildings to focus on water quality and to show them how to develop water management plans and maintain high water quality in buildings. So the little cartoon there, it's a house, and it's just showing that, you know, you've got the water coming in from the utility, and when it gets to the service connection, it crosses over, and then it becomes that legal responsibility of the homeowner or the building owner. I have a cooling tower in there and just a little cartoon of one. And when we talk about building water systems, we also use the term premise plumbing. When we talk about that, we're not talking about just what's in the building. We're talking about any water that comes into that property that could be used for cooling towers, decorative fountains, irrigation, any water that's under the jurisdiction of the building owner or whoever owns the premise or that community. So what makes building plumbing unique? Building plumbing has the same water quality issues that we see in drinking water distribution systems. Very often, the professionals, there is a lack of professionals to recognize and prevent and mitigate water quality problems when they arise in building plumbing. And currently, there are no US regulations that address water quality degradation in building plumbing systems. Except for one case, and Sheldon will be presenting that in our case studies. When we work with building owners and we work with the facilities managers, they're very knowledgeable, they're very good plumbers, they know their systems. The part that we're teaching them is generally how water quality, microbiology, and chemistry come into the picture, and the ways that we use to maintain water quality. So it's not that the building owners don't know what they're doing. We're presenting a different angle to them. And once we start to work with them on water management planning and look at the issues and identify hazards, they get it right away. It's just really a new way of looking at building plumbing and how to manage it. So the issues that make building plumbing unique from distribution system plumbing, there's a high surface area to volume ratio. There are different materials. With lead buildings, there's water age issues. Sheldon's got a great example of that. Extreme temperatures, that may be less so in the Caribbean area, but in parts of the US, like where I live, the water will be at 0 degrees in a couple more months. That's what our water temperature will be. It's still flowing into the plant, but just barely. Low to no disinfectant residual. There's bacterial regrowth. There's proximity to service lines, which is where a lot of leaks will occur. So there's chance for cross-contamination, cross-connections. And then the big thing is aerosol exposure. These diseases that we're talking about now are not diseases because you've swallowed water and it got in your stomach. It's because you breathed in the water and you're being generally infected in the lungs. So these organisms, opportunistic pathogens, pose a logistical challenge because community water systems are designed and regulated to treat pathogens in source water, not to treat these opportunistic organisms, nor would we ever design treatment and distribution to be able to control these. They reside and they multiply in building systems. That's where the focus has to be on management. They get into the water supply because number one, as we've mentioned, they escape treatment, but they can also get in through main breaks, cross connections, or low pressure events. And the key again is that they have to be controlled at the building level. So what do we know? The water quality that your utility provides is good water quality most of the time, pretty much all of the time in a well-operated utility. In a building, it can degrade rapidly, and the number one cause of disease with degraded water quality is Legionnaire's disease. And we know we can prevent this by understanding and managing building water quality. So let me ask if there are questions so far.
Thank you, Jennifer. I think you really laid this out very well, where we are and where we're going with this. I see no questions in the chat. Please, this is to remind everybody in the public and who's on the call, put your any questions in the chat box. And what I always have been told, there's no such thing as a stupid question, so that is not an issue. But I actually one question occurred to me. I remember this was about 15 years ago or so, and it was the first time the Water Authority was asked about Legionnaire's disease. Of course, we didn't do testing here at the Water Authority, and we had to jump through quite some hoops. It was through Jennifer that we found a lab in the States, and it was at that point in time. It was, I think, it was in the really where the academics and the science were to wrap their way around it. We have fast forwarded now, and actually our own lab, believe it or not, is accredited for the Legio Alert method that we use. So we've gone like light years from where we were. Going back to the introduction of your talk, and you said, you know what we do is a typical drinking water testing. We monitor fecal organisms because that is what we do and make sure that the water is okay. Now, all of a sudden, these additional testing methodologies are within reach, and even a small water authority like ours can do this. Should we start including this in any sort of routine monitoring, or what are your views on that actually?
Okay. Yes. As far as, so on routine monitoring, I'm currently developing a project to start doing routine monitoring in drinking water distribution systems in the US. There have been a couple of publications on this, but there's not a lot of data about what levels of Legionella pneumophila are in distribution systems. The work that's been done shows that the levels are very low. And when you look in the distribution system, it's low. And when you look in buildings, you can have orders of magnitude higher levels of Legionella pneumophila. So the focus really needs to be on building control, but it's not enough for, I think, the drinking water industry to say, we don't have a lot of Legionella in the water. It really is on the building side. And we know that, and I know it from my work from decades, but we haven't really demonstrated it. So one of the things that I'm working with utilities on now is developing monitoring programs, where to monitor, what methods to use, what to do if you find it, because you need a communications program to let customers know. So I think and it's done differently in different jurisdictions, but I think we're at a point where utilities should not be afraid to look for it, because simply finding it does not mean that there's any kind of water quality problem, but it's just letting you know what are the background levels. And in places where it's been found, Things like flushing programs have been implemented to in the distribution system to move water through to increase residual, and then the numbers go down, and they often go to non-detect. So there is a way to do this, and I think it's appropriate, but it has to be well developed so that you have a communication plan in place, because simply finding it is not a risk. So I think there's a lot that you need to do to get ready to do it, but certainly it's not something utilities should avoid doing.
Thank you, Jennifer. I think we have our work carved out as usual in the water business, but that is why we're doing what we do. I've got a second question from my good friend Antoinette Johnson at the Department of Environment here, and she says, are there only any other organisms besides Legionella that we should start thinking about monitoring in the water distribution system?
Yes, and I'll talk about that in a couple of slides when we move into the specific organisms. Certainly, Pseudomonas aeruginosa is easily monitored, and there's a methodology that it's called Pseudalert. So it's similar to Legionella, similar product, and we use that in all of our studies. There are some other organisms that are more specialized, so you wouldn't necessarily be able to do those easily in a lab. They're specialized analyses, but certainly to be aware of these things, especially if you're seeing any disease in the community, it's looking at the water quality in those buildings would be the first place to look. Not necessarily the distribution system, but I think it's always wise for the water utility to know what's in their water. And water utilities have been sued in the US for Legionnaire's disease. When it's not a water utility problem, it's a building problem.
Yeah.
So I'll get into the organisms in just a bit. It's a few slides down.
Thank you, Jen. I think what we do, we're going to let you get back to the presentation. There's another question, but I think that may already be answered further down. So why don't we continue with your presentation? Okay. Thanks.
Perfect. So these are just some headlines, and these are taken from actual, outbreaks that have occurred. This is an old slide, but I updated it, and the two updates, you see Texas child dies of rare brain-eating amoeba linked to the splash pad. That happened September 11th. A child died at a public splash park from Naegleria fowleri. We have a handful of these cases every year in the US linked to recreational water. And the one below that, Portland, Oregon Legionnaire's outbreak is ongoing despite mitigation efforts. So there have been a couple of outbreaks in the city of Portland related to a building with a senior living facility. There was an outbreak and someone died. They did a water management plan and tried to clean the building, and there's still disease in that building. So these things are real. Some of these, started out, some of these are dated from a few years ago, but these are ongoing problems, and we see these on a regular basis. So the story of Legionella pneumophila. It was discovered in quotes at a Pennsylvania hotel outbreak and in 1976. And then I was on a research team in 1980 where we developed an animal model to look at the pathology of Legionnaire's disease. At that time, it wasn't known if it was inhaled, if it was ingested, if it infected all the organs. And so I was on a team in the clinical group in pathology that developed an animal model using guinea pigs. This organism is common in the environment, and it's found in treated drinking water in low concentrations. It can grow at elevated temperatures, and this part in red you'll see again a couple more times. It survives and multiplies in water heaters. So 25 to 50 degrees centigrade or 77 to 122 Fahrenheit. So this is one of the problems within the building. If low levels get in, they can survive and multiply in building plumbing. So legionellosis, what is this? This is a respiratory disease that's caused by Legionella bacteria. So the disease that we're most familiar with is Legionnaire's disease, which is a type of pneumonia. The other disease that can occur from the same bacterium, from Legionella pneumophila, is a less serious infection, and it's called Pontiac fever. And it has mild flu-like, cold-like symptoms. And it's not something that in the US we're even tracking this. It's not something that's reportable. Generally, if you had Pontiac fever, it's no worse than a cold, and you probably wouldn't go to the doctor anyway. So Legionnaire's disease is really the disease that we're concerned with. So who's at risk here? Immunocompromised individuals on chemotherapy or radiation or any kind of natural immunocompromised situation. Smokers, a higher risk, older adults over 50. And in the last few years, babies. There have been babies that have become infected in birthing tubs. That's something that's become popular in some subset of women in the United States that want to give birth to babies kind of in a hot tub type situation. And those tubs have been contaminated with water, and the babies, some of these babies have died. About a quarter of the cases that we see have no known risk factors. So it's not necessarily one of these. I've worked on a number of cases where very young, healthy, active people have been infected with Legionnaire's disease and become permanently disabled or died. Where does it grow? We've talked about this a little bit. It grows in shower heads, in hot tubs, swimming pools, certainly decorative fountains have been the cause of a number of outbreaks, cooling towers that we spoke about. And the last picture is a vegetable mister in the supermarket. And there have been cases associated and outbreaks with vegetable misters. So anything that you can think of in terms of generating aerosols, there have been cases associated with those misting stations that are often set up in very hot weather. We see these in the US sometimes, where you can, maybe like at the entrance to Disney World, if you're waiting to get a ticket and get in, they have these misters that keep you cool. There have been outbreaks associated with those. So any kind of misting water or aerosol generating water could be a place that bacteria could grow and then be disseminated. The temperature range here, in temperature is one of the best ways to control Legionella pneumophila. You'll see the ideal growth range is in green. So it's up to, the ideal growth range is 95 to 115 Fahrenheit. And then you'll see that as the temperature is raised, it knocks it down. So at 66 degrees centigrade, the bacteria will die within 2 minutes. And then 70 degrees is suggested as the minimum sterilization temperature. So one of the problems is that most of the time we don't want water at those higher temperatures when it's to be used in a building, and because of scalding issues. So it's a balancing act between using temperature to control Legionella growth and not scald people. The transmission is through inhalation. So you breathe it in through the nose, or aspiration, which is going down the wrong pipe. So breathing in and getting liquid in your lungs. And in 2014, one of the things I said at my lecture for the AP Black Award is that, and I've been in drinking water a long time now, and the first 30 years of my career, we wanted water to be safe to drink. Well, water is now safe to drink, but it may not be safe to breathe. So this woman that's chewing on an ice cube, there have been dozens of cases of Legionnaire's disease acquired in a hospital when patients are given ice chips to chew on because they're not allowed to drink water. They're not eating regular food, either before or after surgery or for some part of treatment. So ice chips are often given to patients. Ice machines are one of the pieces of equipment that can easily become contaminated. The organisms get frozen down in the ice, and when people chew on those ice chips, it's possible that they aspirate or inhale those into their lungs and get Legionnaire's disease. Very often these people die because they're very sick. So Legionella pneumophila is a serious public health risk that we think there are 18,000 cases a year in the US and maybe 10 times more than that. The fatality rate for an infectious disease is high. In an outbreak, it's 5 to 30%, but it's over 50% in hospital settings. And it costs billions of dollars in the US every year to treat it. And there's been a 17% increase over 10 years in the reported cases by CDC. And this is a graph from the CDC. This runs up to 2016, and that number is continuing to rise. So it is considered now, Legionnaire's disease, the #1 waterborne disease in the United States. So over to Antoinette, and what are some of these other bacteria we might want to think about? Something called non-tuberculous mycobacteria. Its nickname is NTM. And that little picture up in the corner, the thing that's got those two kind of frilly things in the middle of that, that's an agar petri dish. It has medium to grow Legionella, and that's actually a plate. And the two things in the middle are NTMs, but the rest of the bacteria on there are Legionella. So they actually can grow out on plates to recover Legionella. These organisms grow and die very slowly, and they're resistant to a wide range of temperatures. Like all of these other organisms, they live in biofilms attached to the surface. These are highly resistant to the disinfectants that we use in drinking water. So compared to E. coli, they're 100-fold more resistant to disinfectants. They include a variety of species. So it's not, NTM are not just one species. And so their susceptibility to disinfectants is different. And we still don't have a lot of knowledge on these in water and drinking and distribution system biofilms. We know they're there, but there's still, Sheldon and I did some research on the project that Henry told you about in the beginning, and there's more interest in these. These are organisms that require specialized test media in order to isolate them. So you certainly could do them in a health department laboratory, but generally an environmental lab like a drinking water lab, it would take some time to be able to set up and look for these in water. Pseudomonas is pretty easy to use. I mentioned the Pseudalert test. Again, this organism, like the others, is found in soil, water, vegetables, in biofilms. You find it in all types of water. It does cause a host of diseases, so skin infections, especially from hot tubs where it might be growing, urinary tract, eye infections. It's the #1 pathogen now that's isolated in hospitals in the United States. And it causes a pneumonia. It's called Pseudomonas pneumonia. And it's actually more common than Legionnaire's disease. So once this organism gets established in a hospital, very hard to eradicate. And many of the strains are naturally antibiotic resistant. As I mentioned, hospital-acquired infections, previously called nosocomial infections. High-risk patients can be on breathing machines. There's infection through catheters, through wounds from surgery, or from burns. That plate up in the corner, that's a petri dish, and that's just showing Pseudomonas colonies. Those were in, the label says tap water, 10 milliliters of tap water, and those are all Pseudomonas colonies that are in the tap water. But let me remind you, this is tap water. It came out of the building in our laboratory in Philadelphia. It's not the water that the Philadelphia Water Department sent to the building. It's the quality of the water that was sitting in those old pipes in our building that had that level of Pseudomonas aeruginosa, which is actually quite a lot of bacteria in 10 milliliters. Pseudomonas aeruginosa disease can be life-threatening, and unlike Legionnaire's disease, it's spread through air and aerosols, but you can also have person-to-person contact or infection through contaminated equipment. That's different than Legionnaire's disease, which is aerosol transmission only. There's no person-to-person or contact through surfaces. And again, infections, the lung infections, are not the result of ingesting drinking water. So, Henry, have we got questions here?
Not in the chat. Oh, hold on.
Okay,
No, just one popped up. May I ask one question first? That came to mind
sure.
actually. So you're in this section. You said it was in the 70s that this was discovered, right? I talk about Legionnaire's disease, and then a
Yes.
few slides later, you said it is definitely on the rise in the United States with that particular graph, and I kind of was wondering. But obviously, before 1976, when they started looking into this, they didn't know that this existed, right? So is it that the cases are increasing that because we quote unquote know better how to look for it, or is it because we have made buildings more complex? There's all sorts of reuse systems and this and that and the other, that this problem in the real is increasing as well.
So that's a great question. What we think is that it's more likely the situation with buildings is that we've got, you know, we're limiting water use. Water conservation has become a very big deal in the last 20 years or so. The CDC doesn't think that it's just better detection, because you know, when someone gets pneumonia, you have to look and see what kind of pneumonia they have, because it could be caused for any number of reasons. But when they tease that out and they look at all the statistics, these are real numbers. This increase is real. It's being seen in Canada. It's being seen in Western European countries and in Japan. So it could be a combination of buildings where the water quality is degraded, older populations, so it's not really clear. What's clear is that it is on the rise. It's not just better surveillance and detection, because that's what was thought initially, that we're looking for it now and we're finding it. Certainly it's been, it was discovered in quotes in 1976 when medical public health departments went back and looked at samples from the 30s, 40s, 50s that had been frozen away. They found that there were pneumonia cases that were Legionella pneumophila cases. It just wasn't an organism that was that anybody had seen before. So it certainly is on the rise, which has led to this focus on building water quality management, because that's where we need to focus. It's not about adding additional treatment at the treatment plant or during production or distribution. The buildings themselves are the incubators and spreaders of Legionella.
Thanks, Jen. I have one question which I skipped on the previous session, and I think actually I just put it there. It said, please expound on the statement about illness from inhalation instead of ingestion of contaminated water. I think you covered that actually very well, where you said the water is safe to drink, but not safe to inhale, right? So we don't have to go back to that one. There is another question that pops up here. Either I'll leave it for both of you to see whether we're gonna answer that now, but maybe that you can cover that in your presentation as you move on. John Haylock here asked, do endpoint filters make any difference? Maybe we pick up on that later on, but you know that by your presentation, that kind of thought has already been planted, like, okay, how do we fix it? So
okay, do you want me to jump on that now, or we can wait till
I don't know, because I don't know what else is coming, so maybe you cover that. What we could do, do you want to continue, and then we can always pick up on that, right?
Yeah, but let's definitely come back to that, because because that's an issue, and Sheldon and I both have some experience with that. So, all right, Sheldon, so I'm going to stop sharing my screen.
Yep.
And you're going to start.
All right, great. Thank you, Jen. So what I'm going to be talking about today is more of the chemical issues that we've seen in distribution systems and in building plumbing systems in particular. And one of the main issues that we've seen is disinfectant byproducts And we've added disinfectants to our treated drinking water to control microbial growth. But one of the unintended consequences of adding disinfectants to the drinking water is that these disinfectants can react with other things that exist in the water, such as organics or bromides or iodides, to form what we call disinfection byproducts, which are potentially harmful. So in the US, the disinfectants that we commonly use are free chlorine and monochloramine. Monochloramine is essentially free chlorine plus ammonia. So it's like adding bleach and ammonia to make monochloramines. And we also use chlorine dioxide. But the ones that are most commonly used are free chlorine and monochloramine. And I believe in the Caribbean, chlorine is the disinfectant that's more commonly used. So these disinfectants that we add to the water to control microbial regrowth in distribution systems can end up forming these disinfection byproducts. In the US, the disinfectant byproducts that are regulated are trihalomethanes. So for example, chloroform or bromoform are examples of those. Or haloacetic acids are also regulated, and bromate and chloride. So there are only a few disinfectant byproducts that are regulated, but there's more and more research that's going into detecting different kinds of disinfectant byproducts. And I think so far they've detected more than 700 different kinds of disinfectant byproducts. Many of these disinfectant byproducts are unregulated, particularly the nitrogenous disinfectant byproducts. And I don't think this would be as big of a concern in many places in the Caribbean, since free chlorine is more commonly used. The nitrogenous DBPs tend to be an issue in systems that use monochloramine. And in a lot of cases, the unregulated disinfectant byproducts can actually be more toxic than the disinfectant byproducts that are regulated. So disinfectant byproducts have a higher production when you have higher temperatures. So in warmer regions of the United States, or sometimes in water heating systems. So like Jen talked about, water heaters are, we tend not to think about the water quality that's in a water heater. We tend to just think about, is the water comfortable for us to take a shower in or to use. But these water heaters are actually really, really nice chemical and microbial incubators. So you can have increased disinfectant byproduct formation at higher temperatures and at higher water ages. So the further we go into the distribution system, you may have more formation that happens. Free chlorine tends to form more regulated disinfectant byproducts compared to total chlorine, or what's called chloramines. And the formation and exposure to unregulated disinfectant byproducts is really not well understood. So this is a really growing area of research. The way that we become exposed to disinfectant byproducts is through multiple routes of exposure. So this could be through oral ingestion of drinking water. It could be through inhalation, where you have volatilization of disinfectant byproducts. So the next time you're taking a shower, you can think about that, or through dermal exposure. So the health effects that are associated with disinfectant byproducts, particularly THMs, include liver, kidney, and kidney cancers, or issues related to the central nervous system. With HAAs, there's an increased concern related to cancer risks, and that's the same with bromates and chlorides as well. There are issues related to anemia, and in infants and young children related to nervous system effects. The other chemical issue that we're concerned about in distribution system have to do with corrosion of pipes or plumbing materials. And we're really concerned about corrosion for three main issues. That has to do with the drinking water aesthetics. So are we going to have, discolored brown water coming out of our taps? We're also concerned about corrosion because of the pipe infrastructure. So you have this example here in this second figure where you have really bad corrosion that's taking place and water being wasted. And we're also concerned about pipeline corrosion because of public health concerns, and we'll get into a couple of those. So you have this example here of a tuberculated iron pipe where you have a decrease in the effective diameter of the pipe in distribution systems, and these are distribution systems that are really well run and have a really low loss of water. Their estimates that about 15% of loss in distribution system is considered that's good. So many of you on the call today work at water utilities and do an excellent job working really hard to produce really good, high quality drinking water. And there's a significant portion of that's wasted due to leaks. In building plumbing systems, particularly in the United States and Canada, where copper pipe is used, you could have issues with pinhole leaks. So these are really tiny needle-like size leaks that happen in copper pipes. Copper is not as commonly used in the Caribbean, so that might not be as big of a concern. So when it comes to corrosion and pipe failures, on the left here, we have an example of what happens when you have a pipe failures in a building. You can have significant damages associated with that. Sometimes these leaks can go undetected for a really long time. So you could have mold that's developing in the building without your knowledge for a significant portion of time. You're also concerned about aesthetic issues, as I mentioned before. So with regards to copper corrosion, you could have blue water that takes place. This is, happens under really specific circumstances. You could also have discolored water, such as orange or red water coming out of your taps because of iron corrosion, or you could have black water due to the release of manganese. And the photo here is just showing what an example of iron corrosion would look like. But the biggest concern that we have with regards to corrosion has to do with public health, particularly lead. So generally speaking, lead is not present in the water that's leaving the treatment plant. It's not present in the water that's in the distribution system mains. The way that lead enters the water is through the corrosion of different lead pipes, plumbing fixtures. In the United States, the main source of lead is from lead pipes. So these are pipes that in some cases were installed in the 1800s or the 1900s up to sometimes the 1950s, 70s, or 80s. And there are about 6 to 10 million of these lead pipes still installed in the United States. Now, 6 to 10 million is a really, really big range, which means that we're not certain where all of these pipes are. So if we're trying to remediate this issue or replace these pipes, the first thing that we're going to need to do is figure out where all of these pipes are. Again, not as big of an issue in the Caribbean because there are not any lead pipes that are there. Another source of lead in drinking water has to do with lead sawdust. That's the glue that we use to hold the copper pipes together. And this is showing an example here of a plumber that didn't really do the best job at soldering this pipe because there's a lot of solder on the outside, and you can only imagine what the inside of this pipe looks like. And another source of lead is from brass fixtures or fittings. And this is actually really commonly used in the United States, Canada, other places, but also in the Caribbean. The way that the US Congress defined lead-free brass was that it had up to 8% lead. So that's how Congress up to 2014 defined lead-free. After 2014, they changed the definition of what is meant by lead-free to mean that it has 0.25% lead. So it's quote unquote lead-free, but not really lead-free. And we've done studies where we found that lead-free brass fixtures and fittings can still have significant amount of lead leaching from them. So you may have brass fixtures in the wash sink spigot that you have, in the hose bib spigot that you have outside, or other fixtures throughout your home, either valves or different kinds of fittings like that. And these could be sources of lead in drinking water. Now, one of the reasons why we're concerned about lead is that it can affect every major organ system of the body. So in adults, we're concerned about brain damage through memory loss, lack of concentration, irritability, and depression. It can cause fatigue and cardiovascular issues. It can cause kidney damage and digestive problems and nervous system damage. And in men, it can significantly reduce your sperm count. And in women, it can cause spontaneous abortions. So this is a really, really big concern for pregnant women in particular. And in fact, in the early 1900s in the United States, doctors would prescribe lead pills to induce abortions in women. But we're really concerned about lead exposure when it comes to children, because that's when they're in their main developmental stages, and the effects associated with lead exposure can be permanent. So we're concerned about brain damage in children due to a loss of IQ. It can result in hearing loss or learning disabilities, decrease body weight, nervous system damage, kidney damage, or issues related to anemia. So this is a really big concern for us when it comes to drinking water and lead exposure. From a societal standpoint, there's this study that was done by the Mount Sinai Children's Hospital, where it just says, if we have a normal distribution here, where we're looking at a population of people, and assuming that the average IQ is about 100, you'd expect that you have 6 million people who have mental issues, about another 6 million people that would be considered gifted. And just by having a 5-point decrease in your IQ points, you're going to significantly shift that curve and significantly increase the amount of people who have mental issues. So you'd have a 57% increase and significantly decrease the amount of people in your population that would be considered gifted. So from a societal standpoint, this can have a really, really big impact for our society. Another concern about lead in drinking water is that human beings are not very good sentinels for identifying lead in drinking water. So this is just a water sample here that has 48,000 parts per billion of lead. There's no safe level of lead in drinking water, but because we can't, it's difficult for us to get to zero, even with the best corrosion control treatment that's out there. In the United States, we have a standard of 15 parts per billion. And this is just demonstrating here that even at really, really high concentrations, at hazardous waste levels, we may not be able to detect lead because it could be dissolved. We're not very good at seeing it, tasting it, or smelling it. So we're not very good sentinels of detecting lead exposure, as opposed to iron corrosion, where it's really obvious when you have an iron corrosion issue. The water is discolored and you have a metallic taste that's there. That's not the case with lead. So in the United States, the way that lead is regulated is through the lead and copper rule. This is one of the most complicated drinking water regulations in the United States. The goal of this rule is to provide the maximum health protection to reduce lead and copper exposure at consumer taps. The rule was first promulgated in the 1990s, and what it did was that it established a sampling process for measuring lead at consumer taps. So before 1991, what they would do is they would measure lead at the treatment plant, but there is no lead that's leaving the treatment plant. So it wasn't a very effective sampling strategy. They shifted that and started to sample lead at consumers' homes, which is where the lead is coming from, and prioritize sampling from homes that were high-risk homes. So those homes that had lead pipes or copper or lead solder. And what they did was to establish actions that must be taken if 90% of the samples exceed 15 parts per billion. Now, remember that I said there's no safe level of lead in drinking water, but they established that if 90% of the samples are exceed 15, then you must take some action. That means that there are 10% of samples that could be a much higher concentration than 15. So this is one of the reasons why this rule is extremely controversial. Because there's no safe level of lead in drinking water, but the rule establishes that you can still have lead, and the system can declare that the water is safe to drink. The testing protocol that's used to identify is used to identify system-wide problems as opposed to an issue at an individual tap. And there's right now in the United States, we're going through the most significant overhaul of this rule in 3 decades. So if you want to learn more about some of the proposed changes that are happening, you can follow this link here and see some of the discussions that are taking place. So next, we're going to be looking at building water issues, looking at some real world examples from work that Jen and I have done, looking at opportunistic pathogen problems, corrosion problems, just general bad water quality in buildings, and then looking at how do we solve some of these problems. So some of the events that can lead to Legionnaire's disease outbreak are outlined here. So Jen gave a really nice introduction in terms of, what are some of the causes of Legionnaire's disease, who are some of the susceptible populations, and how do we control this? So in general, as Jen mentioned before, the water utility does a really, really good job applying the best chemistry and microbiology that we have to significantly improve the drinking water quality. Then we distribute that water through a complicated network in our distribution system, and it gets to the building plumbing system where you can have amplification that takes place due to unique circumstances in the building plumbing system. So that's higher water temperatures. So as I mentioned before, our water heaters, for example, are really nice chemical and biological incubators. You have higher stagnation times in the building plumbing system, and you have scale formation that can happen, free living protozoa. So these are host organisms that the opportunistic pathogens can live inside and protect them. And they also have biofilm growth that can protect opportunistic pathogens and disinfectant loss. After you have some amplification that happens in the building plumbing system, you can have aerosolization that takes place. So almost anything that you do to turn on a tap or flush a toilet or something along those lines is going to produce some small amount of mist. Some things will produce larger mist than others. So the cases that Jen mentioned before of the misters at Disney World or showers will produce a significant amount of mist, and that's where you can have aerosolization that takes place. And then you can have transmission to a susceptible person, and that's where you can have a Legionnaire's disease case that can happen. Outbreaks, the CDC did a retrospective survey where they looked at what were some of the causes of some of the poor water quality problems that we saw in buildings that led to Legionnaire's disease outbreaks. And what they found was that 2 in 3 are due to process failure, meaning that the building didn't have a water management plan. They didn't have a water management plan. About 1 in 2 cases are due to some human error. So somebody didn't do something that they were supposed to do, or they installed a treatment device in the building that they weren't really supposed to have there. So for example, if somebody says, well, I don't like the smell or the taste of the chlorine that the utility put in my water, so I'm going to install a GAC filter at the head of my building to remove the chlorine. That's something that the utility doesn't have any control over. And that's some kind of human error that can cause bad water quality in your building plumbing system. About 1/3 of these cases were due to some kind of equipment failure. And about another 1/3 of these cases were caused by some unmanaged external change that happened. So maybe there was a main break before that caused some intrusion into the building. Maybe there was a cross connection that caused some problems where you had a cross connection maybe with your water system and your fire suppression system. And about half of these are due to more than one of the situations described above. So I'll just stop there for now and see if there are any questions that came up about any of those things. And Jen can also jump in and help me to answer any of those questions that may be related more to the microbiology side of things.
Thank you, Sheldon. I'm listening here to how you and Jen present this. There is such a wealth of information here. So midway, I will say already, thank you very much.
Sure.
I got a good question here, and I think that comes Sheldon's way. It's in the chat. It says, based on your slide regarding lead leaching from brass fixtures, should there be any concern of leaching with the use of brass water meters?
Yeah, so in some cases, you can have lead leaching from brass water meters. So that could potentially be a concern. You can check to see, who your manufacturer was of those water heaters and see what percentage of lead they may have there. Chances are, if they were installed, many, many years ago, those may contain some amount of lead, but that is a potential source of lead. One way to reduce that is to flush your taps, to bring fresh water into your house and get water beyond where the meter is. So one of the first things I do when I wake up in the morning is I might flush my tap until I detect some kind of temperature change. And I said, okay, this is fresh water from the distribution system. And I know I've cleared the plumbing and I've cleared almost out to the water meter. So I'll flush a little bit more. And I know I have fresh water that the utility has delivered to me. So there are some simple remediation efforts that you can use to avoid lead exposure. There's also NSF certified filters that you can use. So you can use point of use filters, or you can use pitcher filters if you're that concerned about it. But the main sources of lead, if you are in the US, are going to be lead pipes and lead solder. And a minor source of lead is going to be from brass fixtures or fittings, but it doesn't mean that you will have zero lead that can come off of those fixtures or fittings.
Yeah, I realized it was my pronunciation. So you answered the question about water heaters.
Mm-hmm.
This question was accurate, but it applies the same to water meters. So as a utility, we put the meter in the system. Maybe the answer is the same, but I think the link here is so we associate a number of these problems with this is stuff that's happening in people's home, yeah, because of old piping, fittings, and you name it. But I think the think through part here is for us as utilities in our system itself. If we have a water meter or other types of fittings, I think about saddles that we use on piping, they're also made out of brass. So that's kind of the question. Do we as a utility need to be concerned about the fittings that we use ourselves? And then the example here that's given is how about water meters? Yeah?
So you say water meters or water heaters? I want to make sure I got it right.
The meter. So where you check the volume that goes into somebody's house.
Yeah, so if there is water that's coming in contact with that brass component and then that's going to be delivered to a consumer, then there's a potential risk there of lead exposure if it's a brass fixture that has lead that's in it.
Mm-hmm. I have this is a broad question, and maybe I'll leave it to both of you. I don't even know whether it's for Sheldon or for Jen. We could park this till the end. We in the recent years we have lead design. Yeah, everybody's familiar with that.
Oh yeah.
And how does that tie in to the whole issue of managing water quality inside buildings? Whether because of the lead we are taking decisions and designing systems that actually do they not take account of the issues that we are discussing today.
I'll start off by saying I'm really glad that person asked that question, because that's a really nice segue for the next discussion. So it's almost like that person was giving us the perfect opportunity for the next part of the discussion. So I really appreciate that question. But the short answer is yes, that those lead buildings are could be a concern, because if we are reducing the amount of water that we're using, then you have the water sitting around in the taps for a longer period of time. That's more opportunity for the disinfectant to disappear and for microbial growth to increase. So there's some kind of conflict that's there where we are strongly encouraging people to, conserve water, but there needs to be a balance between water conservation and water quality. Jen, do you want to add anything to that?
Sheldon, the lead principles are focused on conserving energy and conserving water. In no place did they think about water quality, and that's obvious now. So we've got, it was, we weren't at the table when all the lead stuff happened. So we've seen issues in lead buildings, and I think they're harder to manage. Sheldon's got some great slides from real life situations that he'll show, but it's kind of hard to undo that now, because buildings are, at least in the US, people want lead buildings. You get a lot of points for lead buildings, but they weren't designed with water quality in mind. They were designed with conservation of energy and conservation of water.
But then, Jen, what has been built that is there, and we have to deal with that. Is there, because of these issues that coming up now with in the lead approach, kind of ignoring these type of concerns, that there is a revisitation of how that is done, because it would be a shame that people just put big buildings down, hospitals, offices, and they make quote unquote the same mistakes then. So it really needs to tie back into the rules and lead requirements and whatnot. Is that done?
I haven't had any traction getting on their radar. Sheldon, I think that Mark Edwards tried for a while. Do you have an update on that? I mean,
No.
I think that, they're still going in, they're still not thinking about water quality, and, water quality, both chemical and microbial. I think Sheldon's got a great chemical slide on residuals, but yeah, I mean, it's, when a building's been designed to not use much water, it's hard to flush that building. Flushing is one of our main strategies in maintaining water quality. So no, I don't think that things have changed with LEED.
Mm-hmm. I see one more question. I skip a few. I may pick up on those later. And it's very good. It means there is a great deal of interest in the discussion, and you also evoke quite a lot of thoughts. So I'll take this one. And then it's as Parker says, in the Caribbean, there's a lot of resorts and big buildings.
Yeah.
Should we as utilities take the charge and provide more education to the public regarding Legionella? I think I'm almost giving this to Jennifer on a silver plate,
Well, Sheldon and I have both worked on this, and there's a communications document that we developed probably, Sheldon, 3 or 4 years ago through the Research Foundation, and it specifically is for water utilities to communicate with their large customers and provide that type of education. So it's one of the ways that utilities, the utility cannot do anything about the water quality once it gets into the building, but certainly educating building owners and with, specifics on managing building water quality and Legionnaire's disease. And I think the title of that is, it's communications on Legionnaire's disease and opportunistic pathogens. So if anyone is interested in that, I don't know if it's in the reference list at the end, but I can provide that document. I have everything as a PDF. So if anyone's interested, or if there's, Henry, I could always send it to you and you can pop it on the conference website and it'll be available to people. But it specifically deals with how utilities communicate and educate their large customers.
Thank you very much. I think because you have a lot of interesting other information to share, I think we move on with the next segment, and then of course there will be more time for further questions. Right?
Yeah, and all of these questions were just excellent, and they really lead into the next part of the discussion, both in terms of the question about the resorts, questions about LEED buildings. We're going to talk about some examples of some of those things. So these questions were a really nice segue. So as I mentioned before, I'm just going to be discussing a few case studies that Jen and I have worked on. We've worked on, a ton of case studies, but we're just selecting a few of them. One of them has to do with a resort where there was an issue. So in this case, there was an aesthetic problem. There's microbial growth on the hotel. A hotel's recirculating waterfalls. So you see this waterfall that's here. And the reason why, Jen and her team was called in was not because they were concerned about Legionnaire's disease or anything along those lines, but because they said that, this waterfall doesn't look very good. It looks like there's some algae that's growing and we just don't like how that looks. Can you help us to figure out what's going on there? So there's this greenish tint that was there that's caused by algae. One of Jen's staff, flew down to Florida to try and help them figure out what was going on here. And it just so happens that they have a treatment system that uses chlorine, and the chlorine ran out and nobody refilled it. So it was a really expensive trip just to tell them that you need to add chlorine to the drum. So that was one of the easier problems to solve. But if you look at some of look at this in more detail, this is not just a algae issue that's here. You see that on this picture, there's a mist that's coming off this. And the way that they designed this was to have these grates that helps to create this mist, because you know, they wanted to engineer this in a way to have, you know, the maximum visual effect of that water heater. But in doing so, they're also maximizing how much aerosolization was taking place in this system. So in some cases, the way that we do designs may be looking at the getting water from point A to point B. It may be looking at making something look pretty and a visual effect, but may not necessarily consider what are the public health implications of this. So here you see, this is a photo of the lobby area, entering the lobby, and you see that the public is exposed to this spray or this mist, and you have this cascade that descends to a splash basin near where the guests arrive. So you have all of these guests coming in and getting a nice whiff of that mist as they come in. So that could be a public health concern. You also have this pool, this waterfall here that descends into a splash pool, and you see all of these tables that are right in this area. So this is a perfect location where you're going to have a significant amount of mist that takes place and potential aerosolization exposure. So this is was a resort. This is not necessarily unique to somewhere in Florida. I'm originally from Jamaica, and I've been to some of those resorts in Jamaica and the Bahamas and other places in the Caribbean where you have similar really beautiful designs of these hotels and really nice designs of these water features. They look really great, but the public health implications also need to be taken into account. In the second case study here, one of the things that we looked at was an issue related to discolored water in a hospital system. So there was a 150,000 square foot facility that was commissioned in 2000, so it's not a very old building. This was actually on a Navy base where they provided ambulatory services. And in 2016, they started having discolored water problems whenever they turned on their tap. So people eventually stopped using water in this hospital. And you know, when we went to visit, there are all these people walking around in their military uniforms carrying around jugs of water that they brought from home because you know, the water that they had at the hospital was discolored. So one of the things that they did was that they implemented a flushing program, but the discolored water persisted in some of the locations. So they were able to remediate it in some location, but in others, it didn't work. So one of the things that we did was we went to investigate this issue, and we found that some of the iron valves had to be replaced due to corrosion. So this is, you know, an iron valve that was installed here, and you see that there's a significant amount of tuberculation that was taking place. One of the other things that we found was that there was no discolored water in the cold water system. So this was really isolated to the hot water system. So we're trying to figure out exactly what was going on there. So, and then we also found elevated lead in some of the tap samples. So this photo here, sorry, this video here will show you.
Show me getting wet?
Yeah.
It's not all the way.
Yeah, so that video there shows you what the water looked like coming out of the tap in this hospital system. So one of the things that we're able to figure out here was the cause of the discolored water. So within the system that they had a recirculating hot water system, which is really common in large buildings. So what you'll do, rather than having you know, this person in your hotel or your office building have to open the tap and wait like many minutes, or in some cases hours, until they can get hot water from a distal part of the building where they where the hot water system is installed to where your location is you'll have a recirculating system. So when you turn on the tap, you'll have hot water readily available. Within the hot water system, they had copper pipes, and they also had galvanized iron pipes. And what happens is when you have copper connected to an iron pipe material, and then you have an electrolyte, so in this case, water, you're essentially creating a battery effect. So you have copper that can deposit onto the iron pipes that increases the iron corrosion due to deposition corrosion and galvanic corrosion. So that was the issue, that they didn't have compatible pipe materials that they should have been using in this case. So here just showing some of the sample results that we found. So we collected samples at the point of entry to the building. They had a water softener in the building. So we collected samples at the input and the effluent of the water softener, the hot water utility room, and in several locations throughout the building. And we're looking at copper results, iron results, and lead. And in the US, the secondary standard for copper is 1,000 micrograms per liter. So this is an aesthetic standard, not a health-based standard. The health-based standard in the US is 1,300 micrograms per liter. For iron, the secondary standard, so that's an aesthetic standard as well, is 0.3 milligrams. And for lead, it's 15 parts per billion. And what we found was that there were several samples that significantly exceeded the standards that were there. So for copper, we got results as high as 150,000 micrograms per liter. For iron, the standard is 0.3. We measured samples as much as 72 milligrams per liter. And for lead, the health-based goal for lead is 0. The action level in the US is 15, and we measured samples as much as over 1,000 parts per billion. And this is a system that was built in 2000. So it's not connected to a lead pipe. There's no copper lead solder that's there. The only source of lead in this building is from brass fixtures and fittings. And they were getting samples as much as over 1,000 parts per billion. So some of the other water quality problems that we found in this building was that there was significant chlorine present at the point of entry and in the cold water taps. So that means that the utility was doing a really, really nice job at providing a good residual to this building. In the hot water system, the chlorine residual was relatively low, less than 0.05 milligrams per liter, which is not particularly surprising. The chlorine tends to decay really quickly in hot water systems. At the point of entry, the turbidity was also relatively low, so about 0.3 NTUs, and in the hot water taps, less than 1 NTU in hot water taps that were visibly clear. But in the discolored water taps, the turbidity was as much as 186 NTU. So that's visible particles that's in your water. The other thing that we found was that the bacteria counts were relatively low, which was surprising given the fact that there were several locations in the building that didn't have very good residual, and Legionella was non-detect at all times. So so that was a good result, but at the same time, we didn't collect samples at every single point in the building. So there are very few samples that may not necessarily be representative of all locations in the building. So another issue that existed there was that they had a really complex piping network. I'm not entirely sure why the piping network was designed the way it was, but the main facility was about 300 by 200, and the water supply was supplied from a central plant and came in at this location. And then rather than just having a straight run of pipe that went across, we had this serpentine design of the plumbing system. And again, it's really not clear to us why the plumbing system was designed in this particular way. So what ended up happening was that they had significantly more volume of water than in the system that was really needed. So this really complicates the flushing program that you'd want to implement when you have a complicated pipe network and a higher volume of water sitting in that building than you really need. So in this section of the building, we estimated that there was about 840 feet of pipe and about 190 gallons. In this portion of the building, it was like 182 gallons of water and 955 feet of pipe. Here it is about 845 feet of pipe and 157 gallons, and 965 feet of pipe and 195 gallons of water. And then you had return loops that went back to the main central plant. So the hot water system alone, the hot water system return was 940 feet of pipe and about 26 gallons. So significantly less water was there. So the total amount of pipe length in that building was about 4,500 feet of pipe and about 770 gallons of water. So simplifying this design could have made the building operator's job a lot easier in terms of managing the water quality in the building and also in terms of maintaining good water quality in the building. So what we recommended here was that they should conduct flushing to eliminate the accumulation. But in this case, rather than just opening all the taps like what they were doing before, is to do more of a unidirectional flushing to increase the flow rate and score some of the particles that were there. We also recommend that they improve the material compatibility, so don't have copper connected to iron pipes that are going to corrode your iron even faster, and develop a water management plan. And in the next section, Jen is going to talk about exactly how we'd go about developing a water management plan. For the third case study, we had an issue where we're looking at Legionella in a building. We were originally called in to talk about the Legionella issue in the building, but we also discovered corrosion problems in this hospital. This is a hospital that has more than 400 beds and offers clinical, surgical, and specialty services. The facility is located in California, and this is important because in California, there's a requirement that they have to have 3 days emergency water storage that's there. So the storage tanks that they had at this facility were designed for 3 days emergency supply for an existing building, but also 2 additional future buildings that they hadn't already built. So that means that they had 9 days emergency storage that was there. So this is a water that's sitting around in a large tank and for many, many days. So originally what happened was this system is supplied by chloramine. So as I mentioned before, this is commonly used in the United States, not necessarily in the Caribbean. The hospital collected some samples and found we have detectable Legionella samples and we don't have any disinfectant residual in our building. And they called the utility and said, hey, you know, we don't have any disinfectant in our building. You know, so they expressed this concern to the utility. The utility came out and measured the water they were supplying to the hospital campus. And they said, you know, we're delivering 2.5 milligrams per liter of total chlorine to the building plumbing system, to your hospital campus. Then that water goes into a storage tank. Here, I'm just illustrating the tank as a circular tank, but the tank was actually far more complicatedly designed than this. It was a trapezoidal shaped tank. And in this tank, they had an ozone system that was in the tank. Then the water from the tank went to water softeners where the total chlorine leave the tank was about 0.5 milligrams per liter. So you had significant decay that took place in this tank. And then after the water softener, it was about 0.2 milligrams per liter. And then by the time it got to the building, the hospital, it was non-detect. So some of the causes of the disinfectant decay in the storage tank was from nitrification. So that's something that's going to be unique to systems that are chloraminated systems. There was also really poor mixing in the tank. The tank was not a very well-designed tank. Since the tank was installed, they were never drained or cleaned. So there was significant biofilm growth in the tank. As I mentioned earlier, there was a high water age. So they had 9 days storage of water sitting in that tank. And also the ozone system that they installed was counterproductive because ozone reacts with chloramines to destroy the chloramines. So it's still not clear exactly why they had that system installed. We reached out to the contractor that recommended that design and installation and pointed out to them that, you know, here are all these reports, here are all of these papers, here's the chemistry that shows that this is a really poor design and that ozone is going to destroy chloramines. And rather than saying, oh my gosh, we made a mistake and we you know, recommended a poor design, their response to us was that, well, we've installed this in many other places, which I don't think is a very defensible way to address that problem. So other issues that we identified was that at some points the ozone system wasn't operational, which is probably for the best. There were also corrosion of some valves. So some valves had to be replaced very frequently. So here's an example of one of the valves that was corroded and had tubercles on them. There are auxiliary water heaters that had to be replaced 3 times in the span of 2 years. and there was dissolved copper that increased throughout the building. So as I mentioned before, the copper corrosion issues can impact iron corrosion issues, and that was a similar thing to what we saw in this circumstance. So what we recommended here was that they temporarily bypass the tank and then provide water, clean the tank, drain the tank, and then remove the ozone system that's there. And once they bypass the tank, what we found was that they had pretty good disinfectant residuals that were getting through the softener. So somewhere between 2 and 2.5 milligrams per liter of total chlorine was getting through the water softener. And in the building, now we had, in some cases, good residual that was getting to some taps, but in some parts of the building, there still wasn't good residual getting to some taps. So just because the utility delivers good water quality to the building doesn't mean that throughout the entire building, you'll have good water quality everywhere. That's where taking a deliberate effort to manage the water quality in the building is going to be really, really important. And Jen is going to talk about that in the next section. So as I mentioned before, the recommendations here were to blend the cold water with the domestic, domestic cold water from the hot water system. So they were softening all the water going into the system that wasn't really necessary. Improve the materials compatibility, similar to the previous example. And you're probably seeing a theme here, which is in each one of these cases, develop a water management plan. In the fourth case study here, this was another Legionella problem in a hospital. So there were, this is a 4-story, 500 square foot medical treatment facility that's open not so long ago. So this was in 2014. They have about 42 beds, and it's a medium-sized teaching hospital. And you have a wide range of services, including surgical, emergency, dental, orthopedic surgeries. And there are positive Legionella samples that were detected before we got to this site. So here, this is just illustrating just as a key here. When you see this symbol here, that just illustrates the Legionella concentration. If you see the thermometer that's blue, that's the cold water temperature. The thermometer that's red, that's the hot water temperature. The bottle of Clorox here, that's just indicating, you know, the disinfectant concentration. So the way that this system was designed is you had 2 tanks and you had recirculation between the tanks, and you had copper silver treatment. So sometimes copper silver ions are added to the drinking water to control Legionella growth. So in the tanks, the Legionella was non-detect, and the water temperature was about 19 degrees Celsius. And the disinfectant residual from the treatment plant was about a milligram and a half. Then the water went through a water softener, similar to what was there in the previous example. And the water quality was similar in terms of the Legionella concentration, but the disinfectant residual decreased significantly from about 0.7 milligrams per liter. This was an interesting design because they pumped the water up to the top of the building and then distributed the water. So the water flowed down from the top to the bottom of the building. And what we found was that if you look here, the Legionella concentrations were non-detect where the water enters the building. And as you go further down the building where the water age increases, then the Legionella concentration increases significantly and the disinfectant residual concentration decreases. One of the interesting things that we also found was that the temperature that we found in the building, both in the cold and hot water system, were within the ideal growth range temperature for Legionella. So Jen mentioned before that one of the ways to control Legionella growth in building plumbing systems is through maintaining the good water temperatures. So you keep the cold water cold, you keep the hot water hot. And here, it just so happens that all the water quality samples that we collected, the temperature was in the ideal growth range for Legionella. So we collected several Legionella samples throughout this hospital. So we collected samples at cold water taps, hot water supply and return, cold water sinks and hot water sinks, the blended hot and cold water sink taps. So sometimes you have sinks where it's not 2 different faucets, it's 1 faucet and it's automatically blended. And what we found here was that all the samples, about 38% of the samples in this building that we collected were positive for Legionella. And here on the right is just showing a plate where this is 0.1 mils of tap water from a nursing station. And you see that this plate is covered with Legionella. And here, this is something that Hendrik may be familiar with, as he mentioned before. This is just what the Legionella system looks like. So this is what the how the Legionella measurement looks like here. So here, this is just another illustration of the same building, where we're just illustrating that the water came in here and was pumped upwards and then distributed down. And as I mentioned before, the chlorine residual decreases as the water age increases. So on the lower floors where the water age was higher, we tended to have much lower disinfectant residuals. So this star here is just showing where the samples were collected and where you had low disinfectant residuals throughout this water system. The other thing that we found here was that you had Legionella positives throughout the system, but mostly as the water age increased, we had higher detects of Legionella. So where you have these stars is where we have the detects of Legionella, and this is where you have the lowest water age, and this is where the water age increases. One of the other things that the other pathogens that Jen mentioned, which is this one is a bit more difficult to measure with Legionella. You know, there are several different protocols, but the Legionella system has made it relatively easy to measure these samples. NTM, there isn't as many standard protocols out there and some more specialized method to detect these things, but Jen's lab had the capability to do this. So we also collected NTM samples, which is something that's not as commonly done. And what we found was that NTM positive samples increased as water age increased, similar to what we saw for Legionella. And at the lower floors had more contamination of water than where you had water entering the building. So while we focus a lot on Legionella, there are other pathogens that are out there of concern. In the last case, in the fifth case study here, you know, somebody asked a really nice question about, you know, should we be concerned about green buildings or LEED certified buildings? So this is an example here from a LEED certified building where they had advanced water conservation features. So they had low flow fixtures, low flow toilets, things like that, and new copper pipes. And copper pipes tend to be extremely reactive with disinfectants. So this was a case from some of my colleagues at Virginia Tech, where they were called in not because there was a Legionella issue or anything like that, but because there were taste and odor problems in this new building. So the University of North Carolina at Chapel Hill just spent, you know, many $1 million building this LEED platinum building, and there were lots of complaints about taste and odor problems. So they were called in to investigate what was going on here. The system is supplied by a chloramine disinfectant residual. On the y-axis here, you have the total chlorine concentration, and on the x-axis, you have the flushing time. So what they did was they went to several taps throughout the building and they flushed these taps to see how long will it take us to get a residual that's similar to what's in the distribution system, which is about 3 milligrams per liter. And you see that after about 40 minutes of flushing, where you have that black line at site 4, even at 40 minutes of flushing, you still couldn't get a disinfectant residual that's similar to what's in the distribution system. At the best site that was there, you had to flush for about 15 to 20 minutes before you could get a disinfectant residual that was anything remotely close to what you had in the distribution system. Now, if you think about how we normally use taps and operate buildings, we tend not to just turn on taps and have them run for 15, 20, or 40 minutes. So this is, you know, a flushing exercise to figure out how you'd go about doing remediation. But if we're not looking at a remediation circumstance, if we're turning on a tap because we're washing our hands or something like that, you're turning on that tap for maybe 20 seconds, 30 seconds, a minute, And that kind of flushing, especially intermittent flushing, would not get you to a significant disinfectant residual that's representative of what's in the distribution system. So this is where the water conservation efforts that they had implemented had a significant impact on the disinfectant concentration in this building. On the y-axis here, you also have the total chlorine residual, but on the x-axis here, it's just showing the decay, the disinfectant decay in hours. So what they did was that they collected a sample from a tap and put it into a glass jar as a control, and then flushed each one of these taps. So what you saw in the previous slide, and then they said, okay, let's after an hour, 2 hours, 3 hours, 16 hours, let's just collect small aliquots of water and measure what the disinfectant concentration is. And what you find is that within the water that's in the glass jar, the disinfectant tends to be really, really stable. But the disinfectant that's in those pipes tends to decrease really, really quickly. And in almost all cases, it was non-detect or close to non-detect within 16 hours. So this is because you have copper pipe materials that are extremely reactive to disinfectant residuals, and you also have biofilm that can impact the disinfectant concentration in these pipes. So you had a high water age that was taking place, and you had abiotic reactions that were taking place with these copper pipe materials and causing the disinfectant to decay very, very rapidly. So here, what they did was that they installed an automatic flushing device or flushing system. So the chloramine concentrate, this is going to show the chloramine concentration after the installation of the flushing device. Now, one of the things I want to point out here is this is a LEED certified building, where the goal is to reduce energy, but also reduce water consumption. And now you're going ahead and installing an automatic flushing device. So that's kind of going against what the goals of this LEED certified building is. So here in site one, this is all from site one, and this is just showing what happened after they installed the flushing device. So at site one, before the flushing device was installed, what you found was that it took roughly 15 minutes to 20 minutes or so before you could get a residual that was stable and representative of what was in the distribution system. After about a week of installation, we see that the concentration begins to improve here, and this curve starts to shift more to the left, where we require less and less time for to get a good residual at our tap, and we don't have to flush as much as we were before. A part of this is because of the installation of the flushing device. A part of it is also because the copper pipes are aging over time, and the disinfectant demand associated with these pipes are also decreasing over time. So this is another case study here. This was a study that was done by William Rhodes, who was a researcher at Virginia Tech. He's now a researcher at IRVAG in Switzerland. And he's done a significant amount of work looking at green buildings. So here he just conducted a survey of several different types of green buildings. So the first building he looked at was just a conventional building where you had an 80-gallon water heater. The disinfectant was chlorine in this case, and the hydraulic retention time in the water heater was about less than a day. They also looked at a healthcare suite that was in a green building. In this case, they had an 80-gallon water heating system, a chloramine disinfectant residual, and the average water age in the building was about 8 days. So this is a pretty long water age. They also looked at a net zero energy house where they had a more complicated water heating system, where they had a 160-gallon water heater. And the demand here was about 60 to 80 gallons per day. This was a system that uses free chlorine, and the water age in the building was about roughly 2.4 days in the hot water tanks. And the last building here, this was a bit more problematic, was that they had a net zero energy house, and this was a office net zero energy and water office building where they were using a rainwater harvesting system. So they collected about 3,000 gallons of rainwater in a tank. The demand was pretty low, They didn't have any disinfectant residual in the building, so they were treating it with GAC and UV. But there was no residual that was entering the building from the utility. And in this case, the water age here was 2 months to more than 6 months of water sitting around in these tanks. So you can just imagine what the water quality was like in some of those circumstances. William Rhodes also looked at, within this study, another green building. So this is from the suite that was mentioned in the previous slide. So here they did something similar to what you saw in the UNC study, where on the y-axis you have total chlorine, on the x-axis you have flushing time. And you see that if you're flushing for roughly 20 minutes, you still don't have a detectable disinfectant residual. So if I'm turning on my tap for 30 seconds to wash my hands and then turn it off, 30 seconds to wash my hands and turn it off, presumably you'll never really have a disinfectant residual at some of these taps. In this case, they had to flush for more than 80 minutes at this room before getting a significant residual similar to what you'd see in the distribution system. They did a similar thing here where they had a control sample, which was in a glass jar, where we see that, you know, the control sample was really, really stable. But there's a lot that's going on in the pipe in terms of microbial and chemical reactions that are causing significant disinfectant decay in each one of these cases. So we see that after 6 hours, that all the disinfectant is gone. So you think about when you leave your office or you leave your home or overnight and you're not using water for 6, 7, 8 hours. By the time you get back there in the morning, there is no disinfectant that's left in some of these cases. So those were just some quick case studies that you know, Jen and I have worked on, or other people have also worked on. So I'll just stop there and see if there are any questions that came up, and Jen can feel free to jump in as well, because she was more directly involved in some of these case studies. Any questions?
Thank you, Sheldon. I'm keeping track of the time, so we are going to go to 12 o'clock, and I kind of wonder, I mean, you shared a lot of really good information. I kind of know what the next segment that is coming, because that question is, what can you do about all this stuff? And I'm going to take an executive decision. I'm going to turn it over to Jen,
Okay.
and skip the questions, because that's where all this leads to. Yeah, how can we fix these problems? Okay, so Jen, it's on you.
Okay, I am screen sharing, and I guess I've got to pop down through these. Let me pop quickly. Get up to where I'm going to start. I'll give everybody vertigo here. Okay, so yes, now that we've scared everybody and you know you've got no residual and you've got Legionella and you'll probably never take a shower again, we have to put this back in perspective and let you know that all is not lost, and there's a way that we deal with this type of water quality issues in buildings. And it's through developing a water quality management plan and implementing it. So it starts with understanding your plumbing and how it works, identifying hazards, looking at the risk, mitigating the risk before they become problems, and then we'll go into the how-tos to do this. So we know this with Legionella pneumophila, and you know it now because we've talked about it. You need to keep the cold water cold, hot water hot, but watch out for scalding. Keep the water moving, and Sheldon's given you great examples of water stagnation in LEED buildings. You want to maintain plumbing fixtures and clean hot water tanks. And then the part in red, understanding the system and how to manage that. So that's what we'll talk about next, how you get to managing your building water quality. So when we go in and we work with a building to do a water management plan, it often seems, people think it's very, very complicated, but at the end of the day, this little acronym STAR, these are the things that you want to focus on. You want to minimize sediment, you want to pay attention to temperature, water age, and disinfectant residual. And that's cold water cold, hot water hot, keep the water moving, and keep the system clean. So at the end of the day, that's what it boils down to, even though there are a lot of details in between. So we've talked about some of the complexities with building water systems. Sheldon took you through that. There are specific uses in some buildings like hospitals, medical centers, schools. There's all of the devices that make up the premise plumbing. So we've got cooling towers, boilers, swimming pools, washing machines, dental chairs. Anything that has water needs to be dealt with in water management planning. The plumbing systems are complex because you've got drinking water, you've got sewage, there may be gray water. In large buildings, there's fire suppression. There's potentially recycled sewage that's used for toilet flushing in some buildings. And then in hospitals and senior facilities, you've got vulnerable people because they're older and maybe are immunocompromised simply by age. I'm going to skip over this hospital one and we're going to go right into water management planning. So what we do, if you bring us in to do this, although we've had a pandemic, so Sheldon and I haven't gone to anybody's building to do this for a while. But the first thing you do when you start out, and this is, if you look at the ASHRAE guidelines, if you look at the CDC toolkit for medical facilities, the facility owner or manager has to establish a cross-functional team that has authority, responsibility, and accountability. This isn't something where you say, okay, Joe's going to do this, he's going to take care of it, we're not going to worry about it. It needs to be a team of people that are involved, and certainly facilities people. In hospitals, we have infection control people. We may have environmental health people, but it's a cross-functional team, and they have to have the ability from management, they have to have the authority to make this happen. And where we've seen problems and where these things fall apart, this happened to one of our clients recently. It's one of the examples that Sheldon showed you. The team changed and the boss changed and the whole system kind of fell apart. Because it's a hospital, when the Joint Commission came in to accredit them, they had problems because they had stopped implementing the plan. They had a solid plan, but it just fell apart as personnel changed. And it wasn't one of the things that upper management said, this is something that we have to make sure we have in place. So they're now going back and kind of starting over again. Not with us, but with their part of the plan, getting things back on track. So the first thing is describe how the water is processed and used. We like to see drawings. We like to see actual engineering drawings if they're available. But when the drawings that the team should be using are fairly simple, and this is from the CDC toolkit. You just go through, you start at the top of municipal water, and you draw this diagram out because not everybody on the team is going to be a plumber or an engineer or in facilities. For example, if you have infection control people in the hospital, they're generally nurses and they're not plumbing specialists. So this diagram is something very simple to just show how the water flows through your building. The second thing that you do is do the hazard analysis. So hazards are things that have the potential to cause harm under certain conditions. So we have water, pathogens, and chemicals. Hazards are not necessarily risk. So when you think about risk, it's the probability of something happening times the severity. So the example here, the hazard is going to be falling down and breaking bones. So when we look at this with the risk being probability times severity, if you have an elderly woman, the probability that an adult will fall down is low, but the severity of that, if you're 80 years old with weak bones, the chance of breaking those bones is high. When you look at a toddler, they're going to fall down 25 times a day. So the probability they're going to fall down is high. The risk that anything bad is going to happen to them in terms of breaking bones is low. So we have to, when we go through and we do this risk assessment, each hazard has to be identified by its probability and severity. So things that we see, and we've already talked about these, we have poor flows and stagnation issues, poor temperature control, and then the materials that are used in plumbing. So these are some of the types of hazards that we would look at that we need to characterize. Physical hazards, and this is a problem. It's a real problem with scalding. And when we look at water temperature versus exposure time for burning, and this is on adult skin, you see that 140 degrees Fahrenheit or 60 degrees centigrade is a temperature that will control Legionella very well, but 5 seconds of that temperature on someone's skin will cause second or third degree burns. So while we'd like the answer to some of these problems to be just turn up the hot water and keep it hot, certainly in terms of children or elderly people being exposed to that water becomes also a health hazard through scalding. And let me just pop back. Just as an example, the average shower temperature is about 105. If you like a hot shower, it's about 110. So you can see that if you remember that Legionella chart, that's right in the sweet spot for Legionella growth. The organisms that we've talked about as the microbiological hazards are listed in the top. There are some special organisms that cause what are called another type of hospital-acquired infection. These are they're rare, but they do cause disease particularly in immunocompromised patients in hospitals, and these are all waterborne as well. So the next step after we've looked at the hazards is we design we designate critical control points. So that's a point where you're going to apply some type of control to manage the hazards. So each one of these, for the critical control point, the team looks at 4 aspects. So what are the critical control limits? So for temperature control, for example, in recirculating water, you may decide when you look at your system based on the design that you could get it up to, say, 130 degrees Fahrenheit, but you wouldn't set 130 as your temperature. You're going to want a range. So from maybe 120 to 140, and then you'll manage it within those limits. So you decide what you can do in your system. And this is why you have the team. Everyone looks at it. And then you decide what the limits are. Next is the critical control monitoring method. So how will you do this? So for example, if it's temperature, will someone go around and take physical measurements? Would you have some kind of temperature probe put in some of the pipes? Depending on what your monitoring method is going to be, it will depend on how many sites you're monitoring and then how you want to conduct that monitoring. What's the frequency? And this is something that when the plan gets in place, and these plans are always like living documents. So it's not something you say, this is how we're going to do it. We'll do it that way forever. You have to look at the monitoring frequency. So if you start to monitor, say you're monitoring something weekly in the building, like you're monitoring temperature at different points, and you find after 6 months that you really don't need to do that weekly, that you could back off, then you can change the plan and say, we're going to monitor every other week or once a month. So again, these things are all, tailor-made for each building. They have to be tailor-made by the people that are running the plan. And then the corrective actions. If your critical control limits are violated, then what are you going to do? So an example could be, the disinfectant residual at point of entry and distal taps. If your point of entry is stable and you've got, say, 2.5 milligrams per liter, what can you expect at the distal taps in your building when you've gone through and addressed any kind of problems, like with water age, with flushing program? And this will be different for different buildings. This is not a one size fits all. So the plan is tailored around your building and what can you do within the confines of that. Step 4 is verification. And verification simply means, are you doing it? So it's the confirmation that your water management plan is being implemented as intended, and it's based on the monitoring, service, and maintenance, any kind of records. And the team decides how to confirm that the plan is being implemented as designed. And this is a quality assurance function. So one of the things we saw with this hospital I mentioned recently is that when we left there a couple of years ago, they had all their SOPs in place. They knew exactly what they were going to do. That deteriorated over time. And when it was time for the Joint Commission to come in and accredit them, reaccredit them, they started looking and they said, well, wait a minute, where are all these records? And they actually didn't have those records because staff had changed, leadership had changed, and then they had to kind of, grab what they had. We had a number of consultations with them, and then it was like, okay, you need to get this back on track if you want to be approved and accredited as a hospital. So step 5 is validation, and this is it working? So there's verification. Are you doing it? Validation is your water management plan working? So is it controlling the hazards throughout the building water system? So this is something that you do as on an ongoing basis yourself with your water management plan team. You can do it as a third-party basis. There are consultants that come in and look at this on a regular basis, like maybe say once a year, you'd have someone come in and look at it, similar to like an independent laboratory audit. You can also do something called secondary validation. So this could include in a hospital clinic or surveillance data, results of environmental water samples that you would have tested throughout the building. And this is a quality control function, whereas verification is quality assurance. Step 6, very critical: document, communicate, and keep records. You write it down and you let people know. You have to establish this, and this is an important part of the water management plan. You document it, make sure the owner gets it, the managers, the head office has it. In the hospital, you may want to send it to the health department, to any regulatory agencies. If you're working with a water supplier, you can share the data with them. And basically, when we get to court, and I go to court frequently in these cases, if it ain't written down, then it ain't been done. We don't care how many times you say, I know I did this and these were the results. If you don't have it and you can't demonstrate it, then it's not done. So that's the final, that's the wrap-up step, is getting it in writing and available. This is just a little schematic that wraps all of that together, where you start with a description of the water system, your system assessment, controlling the risks, the verification and auditing, the periodic review. So this is just kind of it's in a summary. And then something that I put together a while ago is kind of the new water paradigm. And we have a lot of utility people in our workshop today. So this is really for water suppliers. A new paradigm is a set of beliefs that replaces another set, which is believed to no longer apply. And I think that when we say water that's safe to drink may not be safe to breathe, we know that. I think that's part of the new water paradigm. We spent decades learning how to make water safe to drink, but that water now may not be safe to breathe. And a big step for water utilities is understanding that the water that you send to your customers is not what's found at the tap in the building. So one of the phraseologies that we've used with American Water Works Association for a very long time are source to tap claims. I was a water supplier back in the 90s, and I always cringed when the chairman of my board would say, the water we produce here is 100% safe to drink at all times. It was safe to drink. We met all the standards, and certainly it was safe, but making that kind of source to tap claim is not something that we can do, especially as utilities, because the utility only knows what's on their side of the meter. And as we've demonstrated in our workshop, once the water leaves that meter and goes over to the service side, the utility doesn't control it anymore. And we've seen what happens to water when it gets in the building. So I think we need to think about source to tap. We need to add the building in there, and we need to start training building owners with the sense that it's part of, there's the multiple barrier approach that we use to drinking water treatment. And that barrier doesn't stop at the meter. That control of water quality has to be maintained by the building owners and operators, so that when it's delivered at the tap, it's still the best quality water that can be provided. And the role that water utilities played, we had a question about this. On the water utility side, we're the water quality expert. The plumbing's different, but the issues are similar. So setting up training and workshops with large customers, and water utilities know their large customers. That's a service that water utilities can provide with very little effort to help their building customers maintain water quality. So there's been a lot of outreach and education on water quality maintenance. Sheldon and I have done a lot of this over the last 5 years. And I tell water utilities that the relationship doesn't have to end at the meter. There's additional ways to support large customers. There's the ASHRAE standards. I'm going to just leave those in the slides for you to look at. The CDC toolkit's available online. And that's all, folks. There are a number of references that I've provided and that will be part of the slide set. And I think if we're 5 minutes over, but I'm happy to stay and answer questions if we have more questions.
Thank you, Jen and Sheldon. I think some people need to run, but we agreed to continue this for a bit. And I see some interesting questions here. Hold on. Yeah, something very practical. The message among other things is keep hot water hot and cold water cold. So, but we are in the Caribbean in the tropics. So our friends from Jamaica says, how do you keep cold water cold in Jamaica? I barely ever use the hot water tap. This is not a trick question, but this is our reality, right?
Right.
So,
I think in some cases, there isn't going to be a good answer for that in the Caribbean circumstance. In the United States, in the South, for example, in Texas and Louisiana, the water is coming into the building plumbing at 30 degrees Celsius. You know, it's already pretty warm, and it's already at these nice growth temperatures for Legionella. So keeping the cold water cold will work in more northern climates, but in the Caribbean, you know, we're blessed with having really nice weather throughout the entire year, but we're also, but what comes with that is having some nice warm water that's coming in where sometimes you don't have to use your hot water heater because it's already warm enough. So that becomes a bit more complicated to try and address in the tropical circumstances.
Yeah. I have another one, and this also brings out the heart of this discussion in our as water utilities. Yeah, certainly in the Caribbean, there is a lot to speak about climate change and how we do the right thing. So the message there is water conservation and whatnot. But then when we look at the plants that you have, in part you get rid of it by more flushing and whatnot. So there are two questions which are wrapped here in one. Hala says, how can we truly, and I think the emphasis on truly, balance water conservation in green buildings with concerns related to water quality? So, so this, how do we find a balance? And then Elise responded there as well. I'm Ms. Hala. Conservation is important to many with the need to maintain quality for public health. So any suggestions are welcome here, because we torn in between those two fields. Yeah.
Yeah. And I think from a communication standpoint, it's also difficult for the water utilities to say, hey, conserve the water, but sometimes it's not good, so flush it. So that's a really confusing to a consumer to tell them that. In some cases, it has to be dealt with on a site-specific basis. So every building is going to be unique. Some buildings may just by virtue of all the people in there may not have an issue. Some buildings may need specific things, so every building is going to be unique. In the UNC example that I provided, for example, they installed this automatic water flushing device that increased the water use in the building by about 1%. So they were able to improve the water quality in that building by increasing the water use by about 1%. So they still ended up using less water than a conventional building, but they just had to flush a little bit more. That's one example. And that's unique to that building. You know, in your building, you may have to do something else. In some cases, you may have to install in-building treatments. We've seen circumstances where people have, with Legionella issues, install filters. That a question came up about that earlier on. So unfortunately, there is not a one size that fits all to address some of these things. But Jen may have a more profound answer than that one.
Well, I don't know more profound, Sheldon, but you know, one of the things, like in LEED buildings, with water being stagnant, it may be, so everybody knows I'm a microbiologist and not an engineer, so I'll talk about engineering design anyway. Maybe we just need to move water. You know, it may be something like, and it could be the same water, like recirculating water, maybe having water, you know, filtered at some point, you know, cold water or hot water. You know, there are probably engineering considerations that, you know, could minimize stagnation and keep water moving. And then if it's the same old water, then, you know, treating it at some point. So you're not really using new water, but you're recycling water through a building. Certainly that's done in industrial processes that I'm, you know, very familiar with, like in semiconductor and pharmaceutical industry, where you have, you know, highly purified water, and it's not wasted, it's recirculated. It's part of the design of those facilities. So there may need to be some things like that that would become part of LEED design, that yes, you're using a little more energy, you're conserving water, you're doing some additional water treatment as needed, whatever that might be, but you're not bringing necessarily new water into the building and then just flushing it down the drain. So those are some of the things I'd like to talk to the LEED people about if we could ever get on their radar.
Yeah, and one of the things that some people are looking into now, for example, with redesigning buildings is, you know, with rainwater systems, we have first flush diverters. So we don't want that first flush of water that has all of the gunky stuff that's in there. So we divert that first volume of water. People have been trying to apply that same concept to water quality in buildings where if the water quality is sitting around for a certain time, you might turn on the tap, and the first several volumes of water that's been sitting there stagnant might be diverted. And rather than using that for showering, where you'd be exposed to lots of aerosols, that water might go towards irrigation or flushing toilets or that kind of thing. Something where there's still an aerosolization that takes place, but to a much lesser extent. And we're still keeping in mind that green concept that we have. So people are trying to move towards working on how can we apply these, still maintain this green initiative while maintaining good water quality. But unfortunately, these are not some of the simplest things to answer because there's conflicts that exist there.
Yeah, but I think you copied it very well. It is not an us versus them type of thing. You know, well, I mean, this also sounds warm and fuzzy, but we all in this together, right? One more question here, quite practical actually. Andrew asks, what is the best way to rid pipes of biofilms?
Oh, okay. The best way to get rid of biofilm is through flushing. So, and I think in some of the case studies that Sheldon showed you, one of the things we always recommend is flushing pipes. You know, and you can do that and look at chlorine residual, for example. So flush pipes till you get an acceptable residual or the highest residual you can get, and scour those pipes out, bring fresh water in and keep the pipes scoured.
Yeah, and one thing I add is that you'll never 100% get rid of the biofilm. If you have moisture somewhere, the biofilm is going to develop. But one of the things that you could do, so the biofilm that develops in the pipe, if it's accustomed to a certain condition, then if water is flowing, the biofilm isn't really going to shear off very much. But if you remove the aerator on the faucet and turn on the faucet to get a much higher flow rate that's coming out of the pipe, the biofilm isn't used to that flow rate. So that will be more easily scoured off from the pipe. But it's not really possible to completely 100% eliminate biofilms. Wherever you have moisture, they're going to develop.
Thank you. So yeah, I miss you sometimes. very practical solutions are easy
Mhm.
to apply. I think that by the level of questions that we get, this is now really a hot topic in the Caribbean. So thank you both for that. I'm gonna wrap it up because we need to be respectful of people's time. From my point of view, I found this an excellent presentation, and I think also was following the chat and also what came out of there. That shows that people are really engaged. So, Jennifer and Sheldon, thank you so much.
Thank you for the invitation.
And I think that also just not me, but everybody else learned a whole lot more today. Just take this away when you go home. The water is safe to drink, but don't breathe it, right?
Maybe.
And on behalf of the Water Authority and the Caribbean Water and Wastewater Association, we're very grateful to both of you that you did not hesitate to accept the invitation to do this workshop, and it has been a wonderful experience today. I also like to thank everybody who tuned in today. I did the registration and all the people responded to emails. It was a very good response. I lost count of how many people we have, but I think I dare to say that probably 100 people were in the session, which is a very good turnout. And also they were not only from the Caribbean region, but they also came from South America and North America. So a really effective morning and a very good way to kick off our conference. Now, the presentation itself, it has been recorded, so it will be posted on our website. That's also where you can find the contact details for Jennifer and Sheldon in case you have questions, or because everybody registered for the email that I received, if you send a question there, I'll make sure that it goes to Jennifer and Sheldon. I thank you all very much and I will have a wonderful day, and I hope to see you all next week at the Caribbean Water and Wastewater Conference. Thank you and have a good day.
Take care.
Thank you.
Bye-bye.
Bye-bye.